Starting from these sections, we're going to how to say apply. I would say yes, apply the what we have learned to more practical situations. So here is the first applications of what we learned about the pure bending, and to the we call the eccentric bending. Okay. And before we proceed this section, you need to know here basic fund review of statics. And for example, if we have the point loading apply P here, and which distance away from D, and we have the equivalent description, say if we want to have a P to say move to A, that's movement due to the arm distance D, that we're going to induce the bending here. So basically the two situations are equivalent. And in this section, we're going to apply these techniques quite a bit often, and to get the things done on the applying the superposition principle. And so we see. So here is the generic, pretty primitive model for describing the common situations of what we call the eccentric loading. So for example, here we pick a section as C here. Okay, we consider what's going on in C here. And in C here, basically here, due to the application, the equilibrium equation, we expect the axial loading in the horizontal direction that is in balance with the applied loading here, as well as apply the P, multiply P with D, we will see that also have the reaction bending applied, that exists in the cross section C here. So under these situations, then this condition, assuming here we consider is completely elastic, so that means in terms of mathematics everything is linear. So these situations can be basically equivalent to, let me consider this free body diagram locally. Okay, so I draw that free body diagram locally. That will be equivalent to that section subject to axial loading plus, that's called the superposition principle. And the same, let me do that again. Pen. So the same sections, and also is under bending. Okay. So this topic basically will induce is we have the sections here. And this, we have the section here, and then let me draw the equivalent, the distribution of the stress. Okay, so for this case, that basically the stress is equal to P divided by A. A is the cross-sectional area of these things. Okay, and for this case, this one is from what we have learned. This is the bending stress. Okay, the bending stress basically we know that is sigma. Let me write it up here. Sigma equal to, in total, the formula is minus my over I, and that is the formula. Or otherwise, you can see the magnitude. Basically, the magnitude of the stress is taking this symbol here. Okay, the magnitude of the stress. Okay, is this one. Okay, so you superpose these things together, then let me ask you, so just like the drawing here, that is the what we learned from chapter 2, and this is what we learned in current chapter, the chapter 4 here. So under this case, you simply superpose, and then you will get the distribution of the bending for this case, for this combined case. Okay, so that is the we call it combined loading. So eccentric loading, basically this is combined the axial loading and bending. Okay, so basically this one is a special case of what we call the combined loading case. Combined loading. Okay, so this is a special case of the combined loading, and this combined loading will be more further explored in chapter 8 later on here. But here we only explore is we have the pure bending, and then axial loading here. Okay, so under this case, let me ask you a question. So for this result, what is the maximum stress in this cross section due to eccentric loading? So this question basically is this: the maximum stress has the magnitude here. Okay, so that is the maximum. And you simply add it up the same sign. This is the tension, this is the tension. So the maximum basically is the P over A, for example here, P over A, and plus the magnitude from pure bending, so My over I here. The I is the moment of inertia with respect to the centroid here, and the Y is the distance measured from here to here, and M simply, the M is the PD, what we obtained here. Okay, so that's the maximum. And then what is the minimum? This is the minimum here. So minimum basically has the magnitude has a magnitude equal to, basically here is again this plus this. Okay, so let me say this one is P over A, and that is tension, and let me use positive to indicate tension, and this is compression, so negative and My over I. Okay, My over I. So using, again, I use negative to indicate compression here. So again, My over I, that's the magnitude here, and Y is a distance measured from here. So basically it depends on the algebraic summation of the two terms, and eventually this could be positive, could be negative, really depends on the number here. Okay, so that is the way to determine this this stress here. So we can take a look at one real situation, the numeric example here. So for this case, we want to determine the maximum tension and maximum compressive stress. So here we pick is the section here. Okay, and then that we pick the sections, then we decompose into these just like we did before. So we pick this section here. Okay, from that sections, again, this is applied loading. Then using equilibrium, P should be equal to 160 Newton, taking the equilibrium of the force in vertical direction. Then M equal to, basically is equal to imbalance with this one. Again, M is taken from equilibrium of the moment. So in this case, M equal to P times D, and that's equal to 104 pounds per inch. Okay, so for this case, then from here with this cross section, so let me draw that one here. So that is a cross section here, and that is under two loading P and N. So we take the superposition principle. This is equivalent to the sections, this cross section under axial loading. So that is our contents of chapter 2 plus the same sections, and this is the centroid here, and then on the pure bending, and this is our contents we learned from chapter 4 here. So for this case, then this one, let me further draw it. So this one here. Okay, so for this case, the bending, the distribution of the stress will be something like this. Okay, for this case, the distribution of the stress will be like this here. Okay, so in these sections is in tension, in these sections, in this portion here, material in this portion is tension, compression here. Okay, and then the magnitude of the stress equal to My over I, and take the magnitude here. Okay, so Y is the distance. Say for example, if you interested the stress at here. Okay, so Y, that means that is the distance between the point where you pick it from the neutral surface here. So that is the distance Y here. Okay, so that's a way, and I is a moment of inertia of the cross section with respect to this one. So with this one, then we can proceed, and then this one we want to calculate. Remember the maximum. We want to determine the maximum stress, and we want to determine the minimum stress. Okay, so again, the maximum stress, if you combine the things together, then that happening on this side here. Okay, let me use a different pen. This one. So the maximum combined together basically is this amount plus this amount. That will give us the maximum here. Okay, so basically that one will be equal to P over A, and that is this amount here. Okay, so and then plus this amount, because here if I use the tensions positive for tension, so this is the positive, and this one also positive tension, so the magnitude is my over I here. Okay, and for this case the y that is the distance measured from here to here, so that is our y. If we're looking into our dimension, then I think in the previous page, what is this one? Okay, so here this is our y is equal to 0.25 here. Okay, so that y equal to 0.25 here. Okay, I think inch. So you proceed the calculations, and then they should be in tensions. Okay, that should be in tension definitely, because the both are positive. And now we calculate the minimum. The minimum basically from here you can see this is the positive and this is the negative. So minimum will happen in here at this point. Okay, at this point here. So depends on the magnitude. So here we can proceed, and this portion again, that is tension P over A. Okay, and again we take the sign convention positive for tension. And now for this amount, that is compression. So the magnitude is my over I. This is the magnitude, and we know this is in tension, so we get the compressive sign here. Okay, so for this case, again, y is a distance from measured from here to here. That is 0.25. Okay, so basically this result depends on the magnitude, and we can implement this one here. Okay, so here, sorry, messed up. But from your slides, you should be see the kind of the point here. So that's a calculation. So we put everything together, and 0, basically this is what I mean here, and P over A here. Okay, so that's a P over A. And sigma n is what I mean here. That is the magnitude my over I, and I explained that is the magnitude, this one here. Okay, so the same thing compressive. So we have those things here. Okay. So now to this point, we have determined the maximum and the minimum stress, and then we want to determine, say, this is an interesting question, how to determine the neutral axis. Neutral axis, by definition, is where the stress equal to 0. Okay, so it's where the stress equal to 0. So how to answer these questions? So basically here, when we basically here graphically we look at the two graphs here. When we superpose together, then we can see that is the cross section, the kind of the distribution of the stress, and here this point equal to 0 here. So from this case, we can come up with more kind of generic calculations. So again, how to do this one in precise calculation here, let me show you a trick. Okay, so let me change the color of my pen to proceed the calculation here. We know for this case, the stress equal to P over A, and for this case, this portion, material in this portion is in tension, and material in the other portion is in compression. And the magnitude of the stress for this case is my over I here. Again, this is the magnitude, and y is the distance. For example, here, if we're interested in this point here, and y simply is the distance between where we are interested to the centroid of that cross section here. That is what we define as a y in our formula here. Okay, so keep this in mind. And then for this case, this is a superposition equivalent to the eccentric loading. So here the stress simply equal to this portion P over A, and this is tension. And now we want to reach the sigma equal to 0 to go to the neutral axis location. And we want to get the sigma equal to 0 to find this location. So you can see when we superpose the two situations together, and we want to reach the sigma equal to 0. So very likely the situations of y will happen in this portion, because in this portion that's a positive plus some negative value that will be making the things probably equal to 0. So here I picked any point y here, okay, and superpose, and this portion is compressive with the magnitude my over I here. Okay, am I asking this term equal to 0 to comply with the definition of the neutral axis? In this case, y is unknown. Once we solve for y, basically y indicate is the distance between the neutral axis to the centroid here. So by doing so, we simply solve for this equation here, and we know the p over a, and that is a 115, and we can determine this magnitude. So in this way, once you solve for it, y should be equal to 0.024 inch. So that means the neutral axis located rightward, okay, to the right from the centroid by that distance here. Okay, so again, to find the location of the neutral axis, and which we stick with the definition stress equal to 0. And so here to come to the very interesting point, for eccentric loading, the neutral axis not necessarily pass through the centroid of the cross section. Okay, so if you remember when we at the beginning of these chapters, when we learned about the pure bending, in that case for pure bending, the neutral axis or neutral surface contains or pass through the centroid. However, because of eccentric loading, because this can be the additionally axial loading that offset the neutral axis. Okay, the neutral axis doesn't be on the neutral on the centroid for eccentric loading, and that is simply due to the additional axial loading in this case here. Okay. And let's take a look at another similar examples here. So here is the kind of the bicycles, the handle there. Okay. So for this case, we're asking the maximum stress is less than 5 times of the normal stress here. Okay. So again, we pick the cross section here, and then in that cross sections, let me draw this one here. So we have P, and here due to action reaction we have P here. Okay, and here is the distance D here. So basically here you see we should have the moments being induced, and M equal to PD. So due to this axial loading, we have P over A, and due to this bending, we have such the distributions. So the maximum occurred is due to the summation of this amount plus this amount. So, okay, that happened here. The maximum stress happened here. Okay, so that basically in that crossing happened at this point, Correspondingly, that happened in here. So this one is asking less than equal to 5 over P, P over A. That's per requirement of the problem statement. So from here you can solve for the magnitude of the D. So basically D will be equal to, you can solve for, say for this case, so for this case, M equal to P times H. So under this case, you can solve for H. H is less than equal to 0.5 times D. Okay, so that is this simple example here. Okay, and now for this one, this is a more kind of a little bit more rigorous, and in the way we're given this T shape, and we need to first determine the centroid. Okay, and like we did, we can tabulate the calculation. So centroid is basically located at 3.8 inch above the bottom, and from there move on, we can determine the moment of inertia respect to the about this axis. Okay, so that is the I here. So I of the whole cross section about this axis is 57, is about 57.9. about. Okay, so with everything ready, this will take a time, will take about 20 minutes. Okay, be careful. And then here for the I1, I2, we simply, again, if you remember our techniques, we have the T shape, and you can decompose into the two simple geometry. This is the area 1, this is the area 2, where we use here. And then from there, if you recall, we apply the parallel axis theorem to complete this one. So that explained by those items here. Okay, if you forgot how to do this one, go back to the previous sections and refer to where how to calculate the moment of inertia of the whole entire cross section about the axis passing through the centroid, and we have the discussion there. Okay, so with everything ready, then we'll look at this problem here. Now the point loading applied on this cross section, basically point loading is kind of point into the paper, kind of applied downward here with respect to this cross section. So we want to determine the stress at point B, stress at point A, and then we want to determine the location of the neutral axis. And again, you could ask me why the location of the neutral axis is not passing through the centroid. Again, this is an eccentric loading. Eccentric loading will offset the neutral axis from the centroid. Okay, so keep this in mind. So we see. So now again, I pick the kind of see the from the side view. Okay, so this is the front view. Okay, so this is the front view, and here this is, for example, let me draw the three-dimensional. So, oops. So this will be look like our sections. So hopefully, okay. So let me draw the three-dimensional. So something look like this one here. Okay. So here is the side view. So it's a front view. So hopefully you see what I'm doing here. So the loading applied simply here. Then basically we can, using the superposition, we can decompose the loading and into such that the loading applied to the centroid, and then plus moment that being induced due to the shifting of the loading point to 1.2 to the offset here. So that is the magnitude of the P multiplied with the arm that is shifting here. So we have the two cases. So again, this case is what we have learned from chapter 2 due to the axial loading. And then from that case, we know the stress simply is P divided by A. And for this case, P is compressed. So this is compressive. Okay, so here this is a compressive. And for this one, again, this is our case of the pure bending. Pure bending is kind of symmetric bending and respect to the centroid. So for this case, that is the distribution of the stress. And in this case, the lower portions and will be in compression. So that means in the lower portion will be compression, in the upper portion will be in tension here. In the lower portion will be in tension, upper portion will be in compression. And the magnitude, so the magnitude here, the magnitude of the stress simply equal to this case. And what is y? Again, if you be interested in, say, calculating the A here, so the y simply is a distance between A to the centroid here. So that's 3.8. For example, you want to calculate stress at point B here for this subsystem, then the y equal to 2.2. Okay. So now for the overall, for the original system, we want to determine the stress at point A simply is the stress of this amount plus this amount. Okay. So here for this calculation, let me change color here. How about that? So the stress at point A simply is the algebraic summation of the two terms. So let me take the negative as the compression and positive as the tension for sign convention. So this is the negative here that indicate that is the compressive stress. And this one is tension, so I put the plus and positive tension here. The magnitude of m equal to 1.2p here, okay? and magnitude, the y equal to distance from here to A, and I is what we calculated from the previous page. So that is the result here. So algebraic sum give us the positive number. So basically that indicating that A here is a tension, a little, okay, not much. And at point B, let me change to the different color. At point B, that is a summation of this term plus this term, that both are negative, compressive. So here at point B, compressive, that is from this one, and plus, I would say plus a negative, because that's a superposition, that is a plus here, and plus a negative, and that's a compressive, so that compressive here. Okay, so I think the better expression should be like this. So the summation of the two negative numbers give us this one. So at B is the compressive. Okay. And now we want to come to the determine the location of the neutral axis. And again, let me erase the necessary term here and to make the things. Okay, so once you have everything here, and I give you a few seconds if you want to take more notes. And otherwise, I'm going to erase the notes here. Good? Okay. Okay, so now we want to talk about how to determine the axial, determine the location of the neutral axis. Okay, the neutral axis by definition here, say, let me call this is a subsystem 1, this is a subsystem 2. Okay, the stress equal to the subsystem 1 stress plus the subsystem 2, the stress from subsystem 2 here. And subsystem 1 here is everything. Here again, I adopt the sign conventions. So system 1 is all compressive. Okay. For system 2, okay, so this sign is the superposition principle. So let me highlight that's a superposition principle, that superposition sign here, and we add it up together. Okay. For the second system, subsystems here, we want to achieve is such that, let me change the color one more time. For determining the location of the neutral axis, the neutral axis by definition is along which the stress equal to 0. Okay, so that is the definitions of the neutral axis or neutral surface on which the no stress. So now you want to say adding the two terms together to make them up equal to 0, to make them the sum of the two terms equal to 0. So you can see here in this subsystem, the upper portion is negative, compressive. So if you added up any point from the upper portion, basically negative together is more negative. It's not possible to make 0. In the lower portion, this subsystem is in tension positive. By adding up the corresponding point here, negative, so very likely this will become in the lower portion will be more candidate like adding the negative and plus a positive sign here. So basically, I would say before we proceed, you should be able to identify the neutral axis should locate in the lower portions of the original system because of the situation, negative and positive together, they will be likely make 0 here. Okay. So now for this case, let me pick up 1 here. So this is the location, and then the distance here, let me call that is a y, where the neutral axis here is. So under that situations, so say per my notation, not y. So let me change the follow up my notation here. So this distance, let me call it a. Okay. So we want to add it up some positive terms. So the magnitude is my. Sorry, not my. I get used to that one. Ma. Okay, the ma over I. Okay, so that is the magnitude of the stress here, and this is the magnitude, and this is intention. Okay, let me add up the sign indicating intention. So the two terms added together must be equal to 0 here. Okay, from this case, you should be able to solve for A equal to 2.411. So that is A here. So that indicating you can calculate the neutral axis, more precise, can be say 1.389 above the bottom, or you can say neutral axis is below the centroid by A. Okay, that is the inch we calculated here. Okay. So again, in one new thing you should have learned so far in eccentric loading is a technique how to determine the location of the neutral axis, and we stick with that one. We know the neutral axis along which the stress is equal to 0, so that means from there we should be able to identify the locations. Okay. This is another similar example here, and probably leave this for your own exercise. And without the details, I think let me go over the what's going on here. Okay. So basically here I draw is the, again, this, let me put into the 3D view, so that this is the 3D view here. Okay. So in this case, this P 10 equal to here, and 10, this one equal to here. Okay. So in this case, we shift the loading respect to the centroid of the cross section here. So basically here, the normal loading total equal to 20. And also respect to the centroid here, the moment you can calculate equal to, okay, contributed 10 with this arm equal to these two terms, contributed 10 with this distance B, okay, and that is come to this and this term here. So the moment equal to the two terms here. Okay. So then further on, this can be decomposed into two subsystems, and P equal to 20, and plus, again, we apply the superposition principle, and that one moment respect to the centroid, and M equal to whatever being calculated there, 10 kilonewtons multiplied 0.025 minus B here. Okay. So that's the M. So from here, you superpose the two things together, and similar to the previous concept here to answer this question. Okay. This is another similar example here. Let me see. Okay. So for this case, we have the 3 point loading possibly applied at 1, 2, 3, and then with these locations. So the first question, if the two loadings are applied as shown, then we want to determine the stress. So basically for the first case, then that's simply equal to this. This is the 3 loading, 15,000 pounds. Okay. So this one basically equivalent is to 45. So this is our chapter 1, the chapter 2, the axial loading case. So basically the stress equal to magnitude of P divided by A. The magnitude here is 3P. Okay. So that is 45 and times 10 to the 3 pounds divided by whatever the area. The area, for example, here it didn't show. Okay, area here is 8 times 3 inch square. Okay, so that is for A. It's very simple, simply axial loading. For problem B, and say the loading at point 2 and 3 are moved, so basically the case like this one. So let me erase the, okay, let me use the different color and to save the notes here. So basically this case will be equivalent to is this one. So that is the top face here. Okay. So that will be equivalent to the P applied here, and also P multiplied with this arm will induce a moment, and equal to P times 5 inch. Okay, so here again we apply the superposition principle. So let me take this, okay, input into 3D here. Okay, so that equivalent to is a P equal to 15. So P equal to 15,000 pounds. and plus the superposition principle here, and this is a centroid, and we have a moment here. Okay, so moment equal to 5 times p. Okay, moment equal to 5 times p. So after this kind of decomposition, then you can proceed. Then the stress will be equal to, for this case, p divided by a, and this is compressive. Remember, we take the sign using the negative for compressive and superpose. Okay, and for this case, whatever. So here we, for example, point A. So point A is here. So point A is here. Okay, so the point A, you can see for this case, these portions, the left hand side, this will be in tension. Okay, so this is point A here. So the magnitude is my over I here, and we know at point A that is in tension, so that is tension for a positive sign. And here, what is y? Y is the distance from A to the centroid. We measure here from A to centroid, that is 4 inch. Okay, so that's a way you determine the stress at point A here. In a similar way, we can, again, the stress at point B, let me change the color. The stress at point B, again, that is superposed, and P over A, again, that is for this subsystem, and that's compressive. Okay, and superposed, and that is a sign here. And now the magnitude, my over I, there's a magnitude, then we decide. And B is here, so basically B is here. Okay, so in this portion, that is in compression here. In compression, so here you added the negative sign to indicate that is compressive stress. And y at point B, and that's distance from B to the centroid of the section, and that is 4 inch. Okay, so again, you implement this one, you can get B. So that is the detailed calculation for you here. Okay, let me see. I could have made a mistake here. Okay, so I think I made a mistake, and before I identify the mistake, I want to give you 5 seconds to see whether you can identify the mistake I made. 3 seconds, 2 more seconds, 1 more second. Okay, so here is a mistake I made, and let me correct it. I made a mistake here. So this system, basically, if I shift the loading to here, then of course, like this one, then this loading multiplied with this arm should have induced the moment not in this direction, but in this direction. Sorry, that is a mistake I made here. Okay, so that should be the one in this case. Then under this case, you can see the distribution of the bending, the subsystem will be something like this. So this is a cross section here. Okay, so this is the 3D view here. So now this is the centroid. The moment is like this way. Okay, like we corrected here. So the distributions of the stress will be something like this. Okay, so that would be like this. So that means, let me correct, then in this segment, this should be tension, and this one should be compression, like we draw here. Okay, so that is the way it is. So in this way, I need to correct my calculation. For point A, that is a subsystem, the stress from subsystem 1, that is the same as I did before. For this one, you can see right now the A is in compressive region, so here that should be compressive. Okay, the sign is a superposition sign here. For point B, that is right now in tension, and so here that should be in tension. Okay, so I need to correct my mistake, and I think this will be the good lesson for everyone to pick. And yeah, so that is a detailed calculations for your reference.